Hello, everybody. This is Marina from the outreach group of the Magic Collaboration. And today we have this live event. It's the first time, so I'm very excited. And okay, let's start with saying what is Magic Collaboration, okay? So magic, the word magic stays for, I will show you this, Major Atmospheric Gamma Ray Imaging Cherenkov telescopes. So what we do is to explore the sky and detect gamma rays from distant sources. What are gamma rays? They are photons, so basically normal light. But what is different from the normal light that we see in galaxies is that they are very, very energetic. So they are not possible to be seen with the naked eye. You need very powerful telescopes to see them. Then, okay, we observe this light coming from distant galaxies and we analyze this data and we try to understand these very violent processes that can produce such energetic photons. And the Magic Collaboration is a big collaboration, we can say. We have like 150, but maybe more researchers working. Okay, there are not only researchers, we also have technicians, people that takes care of technical aspects of the telescope, administrative staff, and so on. But anyway, around 150 people are working to keep these telescopes working well, detecting our favorite sources in the sky, and learn more about our universe. Researchers in Magic, they come from different countries, of course, and they all work together to collect important results for the community. And of course, these results, we want to publish them because it's important that we share what we discover with the scientific community and with people that can say, okay, these results are good. So what we do, we publish a lot of papers every year, and now we want to start these live events in which you can meet the people that really wrote those papers. So yes, astrophysicists, they are, okay, not normal people, but they are real people, and we can talk to them and ask information about their work. So today we start with a very nice paper, which is just published on Physical Review Letters, which is an important journal in our field. And okay, the title of this paper is Bounds on Lorentz Invariance Violation from Magic Observation of GRB 190114C. So okay, it's not very easy title. In our advertisement of this training, we wrote Einstein put to the test. Okay, this is the short title. And we have in studio corresponding authors of this paper. So the people that really worked on this data and then they really wrote this paper. Actually, we have 4 corresponding authors, but we couldn't gather all together today. So I will introduce you 2 of them, and then, of course, maybe in another occasion, we can also see the other 2. Okay, and so here now with me in studio, we have Tomislav Terzić from the University of Rijeka. So I'm adding him to the stream. Here he is. Hello, Tomislav.
Hello, Marina. Hello, Marina. Hello, everybody.
Hello, how are you doing?
Perfect. Very well.
IKEA office, you too, I can see. Okay, so, well, and with us there is also another corresponding author of this paper, which is Giacomo D'Amico. Hello, Giacomo.
Hello. Hi, everybody.
Hello, Giacomo, where are you?
Good. Fine.
Yes, you are in Munich, right? So the banner is correct. Are you there? You are in Munich in this moment?
Actually, in Italy.
Ah, you are in Italy.
No, actually
okay.
in Italy.
Okay, well, anyway,
Yes.
you work at Max Planck Institute for sure. And in this moment, you are in
Yes.
Italy. Okay, very well. So let me show you just a second a picture with all the researchers from Magic. You see we are a lot of people. I just wanted to show you this picture because I like it very much. So let's go back to our event now. Okay, so let's talk about this paper, guys. Are you ready?
Yep.
It was published just yesterday, so I know it was published at 6 o'clock European time. So, okay, bounds on Lorentz invariance violation from magic observation of GRB 190114C. Okay, now let's start with this, with the title. Tomislav,
Shoot.
tell me, how can we explain to people what is this GRB 190114C? What is this dataset? Why is it so important for us?
Well, GRB stands for gamma ray burst. And gamma ray bursts are very sudden cosmic explosions when in a very, very short time, it could be from less than a second up to a few minutes, or in extreme cases, maybe a few hours, huge amount of energy is released. Usually there are two types. One, which we call a long GRB, and we call it long only because it's longer than 2 seconds. So something lasting 2 seconds or more is called long. Then this should give you an idea how brief, how sudden these events are. So these long GRBs are, we believe, they happen when a massive star collapses to a black hole. And these short ones, short GRBs, are usually connected to merger of two neutron stars. Anyway, a huge amount of energy is released in a very short time. And of course, we're interested in understanding what's going on there. However, in our case, we wanted to use these data for another study because these Lorentz invariance violation, I think Giacomo will tell more about that, need well, strong signal, bright source from a long distance with very high energies in the gamma rays. So this is what we focused on in this study. In this particular GRB gamma ray burst, it's called 1901-14C because it was detected on January 14, 2019. And usually those GRBs are detected with satellite detectors because we cannot predict them. We don't know when or where they're going to happen. And satellite detectors usually have huge field of view, so they cover a huge portion of sky.
Yes,
and
very
we don't.
well. Look, yes, this is great, but I think I can help you in explaining this with the video, okay? So
Sure.
what you said is fantastic, but I think we have a nice video which describes how a GRB gamma ray burst happens, okay? So let me try to share it. I think you know this video. It was produced by our outreach at MPI Munich, okay? Now I will try to share. Okay. And this is the video. Do you see it?
Yes.
Okay, so here something's going to happen, right?
Yeah. So this is a gamma ray burst happening.
Yeah. Okay, it's we don't know if it's exactly like that, but okay. So we have this giant explosion, as you were saying, right?
Yeah. So this is a very sudden explosion. It happens in a very short period of time.
And the satellite, yeah.
And these are the satellites. So they cover a huge part of the sky at the same time. And when these things happen, they can see them. in our case, we cover only a small portion of sky, only a few square degrees, and we cannot. Well, the probability of detecting them accidentally is very small.
It's very small because they are very sudden. And look,
yes,
I stopped
and we don't know
the
whether
video.
they're going to happen. So when a satellite sees one of those, it sends a trigger like this and saying, "Guys, something's going on there. Can you maybe try and see what happened?" And then we reposition our telescopes automatically, which happens in a few tens of seconds. Usually, in this case, in some 30 seconds, that we received this trigger and started observing.
Yes, look, I stopped the video because this is what we see in our magic counting house. Then we get when shifters are observing, then they get a trigger, you know, as you said, from some other telescopes that some gamma ray bars could happen. And so immediately everything is stopped in the counting house. And then the telescope, they have to be pointed to these gamma ray bars. So this is what shifters say for a minute in their computers in the counting house, right?
Yes, and from my personal experience, I just have to add that I love these GRB alerts because a big red screen appears and says, "Don't panic." And,
Don't
and
panic.
of course, I panic every time. I had a heart attack a few times.
And the noise is like bah, bah.
Trumpet or horn or something.
Yeah.
So of course you panic, but it's a good reason to panic, I guess. So the reason why I want to observe them from the ground with Cherenkov telescopes is because we observe in a higher energy range compared to the satellites. So satellites see one of these per day on average. But they see it in up to 100 GeV or maybe a few hundred GeV at tops. But this one that we saw from the ground, we saw events up to almost 2 tera electron volts. So at much higher energies.
Okay, yeah. That's for sure. So we have this fantastic data set with this very special event, the gamma ray bars, that provided us with the very special super energetic photons, right? Okay, so this is like the first thing in the paper. So we know where this data set is coming from and why it's so important to us. So look, I have the paper here. So, okay, let's start with the introduction of this paper. We know that we are using gamma ray burst data, okay? And magic data about these gamma ray bursts are so important. We explain why. Now let's go to the introduction of this study. We start like quantum theory and gravity are expected to merge at around the Planck energy. And okay, there is this value of the Planck energy into a joint yet unknown theory of quantum gravity. Okay, so there is a lot here as first sentence of this paper. So, Giacomo, let's try to explain to normal people what does it mean? What is quantum gravity? Why with this result we can constrain quantum gravity? Okay, now it's your turn.
Okay. So essentially, we have this beautiful theory of general relativity, which is great to explain how energy and mass interact with space-time, creating a phenomenon that we commonly known as gravity. But nevertheless, physicists suspect that general relativity is not the most fundamental theory, and that there must exist an underlying quantum mechanical description of gravity, because we know that we, on the other hand, for the macroscopic world, in order to describe the macroscopic physics, we use quantum mechanics, which is nowadays we don't know how to merge the two theory. On one side, general relativity; on the other side, quantum mechanics. There are different models that try to merge these two theories, and according to one of these models, we should accept that at the energy, at very high energy, which is called the Planck energy, something weird must happen, and these weird things that must happen is that the speed of light is not anymore constant. This is the novel, yeah.
This is the Einstein
Yes.
the test. Okay. So we are looking for this violation, right? For these inconsistencies. Yes. And are they easy to be found? What do you think?
No. They are absolutely not easy to find here on the Earth with our experiment, because the effect that we are trying to look for is very, very small. What we need is a kind of process that magnifies this effect, and this process is actually the big distance that these photons have to travel in order to reach the Earth. And so let me share, I don't know, probably it's better if I share my screen to show you.
Yes, sure. Please share your screen. Yes.
Yeah.
Yeah. Okay.
So this is just a brief introduction to the effect that we are looking for, which is called generally called in physics Lorentz invariance violation, because according to general relativity, the special theory of Einstein, if we have two photons at different energy, we should expect to observe these photons at the same time, assuming that they were emitted simultaneously. But according to some models of this theory that I talked before, of these models of quantum gravity, this is not anymore true. We have you need to accept a kind of delay between these photons. So essentially, gamma ray bursts are like a race among photons of different energy, and you're trying to detect this time delay.
So they are perfect to this kind of study, gamma ray
in
bursts,
the photons that you observed.
So we would like to have more gamma ray bursts, right?
Yes, because Yes, yeah, because
one is not.
Because of course, one problem is that you cannot know if these photons were emitted simultaneously. That's one the biggest problem in this kind of study. But with gamma ray bursts, you can make the last for a very few seconds, so that this helps you in studying this energy dependent time delay.
Okay, I see. So you want to find to find the Lorentz invariance violations possibly in this data set coming from a gamma ray burst. Okay, and Tomislav, which there are different ways to test Lorentz invariance violations, right? And in your paper, you used one of these approaches.
Yes. Well, what Giacomo explained is that if this Lorentz invariance violation is well, if it occurs, if Lorentz symmetry is violated, then this could have different influences on photons, on gamma rays, might also have different influences on other particles like neutrinos or cosmic rays or gravitational waves. And here I'd like to give a shout out to cost action that we have, CA 18108, where all experimentalists doing with these different messengers that we call them are joining the theoreticians to study this together. I'm sure there will be soon some results already came from this action, this collaboration. But in this case, we focused on gamma rays alone because this is what we do. And the thing is, if gamma rays, not all gamma rays are propagating at the same velocity, or we actually, like, maybe I can share my screen to explain this better. Yes, cost action.
Yes,
right.
I was sharing the cost action webpage, because you talked about these important synergies between what is particular of this action is the synergy between the theoretician and the experimentalist, which is not always very easy to get.
Doesn't happen that often.
But okay, yes, please share your screen and tell us a little bit more about quantum gravity and about your result, of course, in order that we can understand.
Yes, so actually in our paper, this is equation 1 that I wanted to show you. I don't know whether you can see it. It's right here. So this is where we start usually from. This is a very simple way to parameterize what this effect that we are looking for, what Giacomo was talking about. And if Lorentz symmetry is fully preserved, if nothing strange happens, then this whole thing is just 1, or there is no this sum here for photons. So simply energy squared equals momentum squared, and here we assume that speed of light is 1, which is a common thing to do. Yes. Now, what we introduced, just a way to parameterize these things and study them, is to introduce this small variation, small modification in this dispersion relation. But now once you do this, then whole hell breaks loose, really, because this can influence the velocity, speed of light, depending on the energy. But it can also have some other consequences, like it might affect interaction of particles. So it might happen that gamma rays, when they interact with other particles, this interaction is somehow different. It's more probable or less probable, things like that. In this paper, in this study, we focus only on this velocity, the speed propagation. And we only test time of flight. Yes, we test whether photons of all energies travel at the same speeds. How we do it? We measure arrival time of gamma rays from a source, in this case, this gamma ray burst, and then we compare those. One problem with this is that we can measure quite precisely the arrival time. What we don't really know is the exact emission time. Mm-hmm. People who study these sources, they have models that describe them. Unfortunately, they are not that precise, so that we can say, okay, this photon was emitted at this time precisely, and this other photon was emitted at this other time.
Well, I guess it's not anything to do.
Not at all.
Yeah. Well, okay, I see. So you use this time of flight method.
Right.
And listen, Giacomo, reading your paper, it's clear that you were very, very precise in testing the light curve. Okay, let's show this light curve. Listen, since Tomislav, you are sharing. Okay. Okay, yes, here we have this light curve, which is, of course, it gives information about the flux of photons that we catch from these gamma ray bars. So from this light curve, okay, Giacomo, maybe it's better if you explain this. What do we see from this figure? Giacomo is a little bit frozen, but yes, in the meantime, we can see from this figure that we didn't catch the peak, I mean the maximum emission of the gamma ray burst, but with magic we could see like the afterglow in some way of these gamma ray bars. So in this figure, you see points that correspond to the flux of photons that we detected from this source. And Giacomo, in this paper, you studied this light curve, and to be very precise, you used two different models, right? Can you tell us a little bit about this, very, very short, if it's possible? Now you can hear me now. It's okay, because before you were a little bit frozen.
Yes.
Okay, please.
Yes, now I can hear you. So essentially, yes, we were making in this paper two assumptions. The one is let's say it's very simple. We are just assuming that all photons that we observe were emitted after the alert that we received from the space telescope. Because as Tomislav was saying before, we didn't observe the full emission by this GRB, but just we start observing after 60 seconds after we received the gamma ray burst trigger the space telescope. And instead, the second assumption that we made about the light curve of this gamma ray burst is that the other assumption is just the theoretical one. We simply use the conservative estimation from models regarding what has been observed at lower energy, lower relative to the one that we observe with our magic telescopes. So this is just in a nutshell the assumption that we did for our work.
Guys, something happened with the internet connection. So this is very live. Please, Tomislav, come here. Okay, we are lucky anyway, because Terzić is working in my institution. So he came running from a long distance, and now he's here with me. So, okay, guys, I hope nobody disconnected because of this. So we are back again. So thank you so much, Giacomo. So using two different models is very important, right? Because in this way, we can be sure that our study is very solid. But wrapping up the situation, so like conclusions of your paper, Tomislav, so did you find those Lorentz invariance violations or not?
No.
No.
Well, first of all, we don't know whether they are there or not. And if they are very difficult to find. What we did do, though, is set a very strong constraints on this violation. So if it is happening, it's happening at some very, very high energies, more than we could measure. And what I would say is maybe the most important thing about this paper is that it was the first this study of Lorentz invariance violation done on gamma ray burst data with Cherenkov telescopes. And with the Cherenkov telescope array, CTA, coming online soon, in a few years, hopefully, with that array, we'll be able to see many more of gamma ray bursts, and then we'll be able to repeat this study on new sources. Hopefully, we will even catch the beginning of the flare with the peak, maybe even higher energies, see more variability in the flux. Yeah, that will be pretty cool.
Yes, so we are looking forward for Cherenkov telescope array, so we could have, more data to analyze. Okay, I know that you are more theoretical guys, so you are more into interpretation, but I want to have things to analyze. Okay, so very well, guys. So we are going to the end of our first event. I hope it was okay. I'm sorry for this disconnection
Somebody
problem.
wants to measure my mass. Please don't do that.
Okay, come on, Dominic, you don't ask a guy to measure his mass like that. Okay, so
Close to a black hole. Sorry.
okay, okay, please.
So, okay, guys, I want to remember here that there are also other corresponding authors, in particular Daniel, that now is on shift. So he's on La Palma, you know, and so the poor guy is leaving because he's going to work during the night. So he couldn't be with us because he needs to observe tonight. And we also have Cedric, which is a very young researcher, and he worked a lot for this paper, but he is moving now in France because he's contracted at the University of Padova. So he's going back home, and you know, in this moment of COVID panic and situation, it's not easy to move, and so we couldn't have him today. But we hope to have them soon and to ask them more about this very interesting topic. So, okay, it was great to talk to you today. I don't know. I'm sorry we couldn't answer to many questions, but okay, stay tuned, and we will have soon other events with other magicians. Bye.
Bye.
Bye, everybody. Bye. Ciao, mamma.